All right, here is another complex circuit problem solved. Sometimes these are called RC circuits because there are both resistors and capacitors in this circuit. So this is an RC circuit problem. Go ahead and read this through, pause it, and we'll work through the solution. So the first bit of this problem is actually a little piece of theory. Um, There's a few ways to describe this, but when you read or hear that the circuit is allowed to reach a steady state, sometimes it's called equilibrium, or sometimes they even just say after a while. What they mean by that is charges have been allowed to build up on this plate until the point where there is no more motivation. So this is a connected circuit now. If this switch is closed for a while, once the charge is built up on this plate, there's a certain point where there will no longer be any motivation for charges to flow down this pathway. You could almost think of it being like a water tank filling at a certain point. If this tank fills at a certain point, the water levels would be equivalent, and there would no longer be any motivation for the water to flow from left to right, if that makes sense. That's sort of an analogy. So while a capacitor is charging, current will flow. But once it has the same amount of, you could even just think of once it has the same potential as the battery on that side, there will no longer be any more current. So the sort of theory bit is once it's reached steady state, you can picture this as being resistance infinity. What does that mean for this problem? It basically means once this reaches steady state, if this has infinite resistance, i.e., like I said, there's no more motivation for current, there's no more motivation for electrons or electromotive force, this is kind of shut down. You can picture this being not even a part of the circuit in this question. So they've incorporated a theory bit before you start the problem. The question is really asking, once you know this in your mind, after steady state is reached, capacitors reach infinite resistance. Now let's go and figure out the real part of the question. What is the potential difference across resistor 2? This is not an easy derivation necessarily, but I think the thing that you should know is that the total voltage across the battery should be, or the cell, whatever the power source is, should be equivalent. If I followed one pathway, let's say this pathway here, then this voltage drop and this voltage drop should be the total voltage drop of the battery. It's almost like saying the sum of the voltage drops should equal the voltage drop of the power source. So that's your first starting point. From there, there's a couple simple rearrangements here. If I'm solving for that voltage drop across resistor 2, I would quickly get this. And again, this epsilon, this E, this Greek letter is just what they are calling the electromotive force of the battery or the EMF of the battery. So you end up in this spot. And if you could get here, that really is half the problem because two more substitutions and I will end up with an answer. From here, you can use Ohm's law, and you'll notice none of these answers have V1 in it, or delta V1, or the voltage drop. But I do see some other things. So I'm going to go ahead and just assume that because there is no delta V1 in any of these responses, I'm going to go ahead and get rid of this. How could I express this in another way? Well, if you know Ohm's law, we could quickly turn that into voltage times resistance. So the current times resistance. So the current through resistor 1 times the resistance of resistance 1, and I get here. Starting to look more and more like answer D, but if you still weren't sure, going one step further would get you to a point where you could actually make a cool realization here. I1, this value, I1 in this case is actually the same as the total current. So this current through number 1 or resistor 1 is the same as the total current or the current through the battery. Anywhere along this section of the circuit here would be total current. So I'm going to make a little substitution here and call that total current instead of current 1. And then this problem's done because one final substitution, and instead of total current, I'm going to again use Ohm's law. I'm just going to do a little side tangent here. Total current would be the total voltage divided by the total resistance. And they say in the question here, it's the total resistance. Sometimes we call that the equivalent resistance if we're referring to more than one resistor. Subbing that in for total resistance, and I'm left with answer D, because I would have EMF times resistor 1, or resistance of resistor 1, divided by the total resistance, which we're calling the equivalent resistance. And that gives me D.